Welcome, fellow travelers of the cosmos, to today's exploration into one of the most mind-bending mysteries of our universe. Whether you're a truck driver navigating the endless highways under starlit skies, or you're finally settling down after another demanding day at the office, you've found your way to exactly the right place. This is your sanctuary, your moment of peace, where the complexities of existence unfold in gentle, soothing waves of understanding. I invite you to share where you are in this vast world of ours. Drop a comment telling us your local time and which corner of Earth you're calling home tonight. Perhaps you're watching from a cozy apartment in Stockholm as snow falls silently outside, or maybe you're listening from a warm evening in Brisbane where the crickets are beginning their nightly symphony. Wherever you are, you belong here. If this journey through the fabric of reality helps ease you into that blissful state of rest, please consider leaving a like or subscribing. These small gestures help others discover this peaceful corner of the internet where science meets serenity. The visuals accompanying our exploration tonight will enhance your experience, but they're merely companions to our story, not requirements. Close your eyes whenever you feel called to do so. Let your imagination paint the pictures as we venture together into the extraordinary. Tonight, we're embarking on perhaps the most fascinating journey possible, one that takes us to the very edge of what time itself can endure. We're going to discover why the universe has built into its very foundations a speed limit so absolute, so fundamental, that when we approach it, time itself begins to behave in ways that would seem like pure magic to anyone living just a century ago. Imagine, if you will, that you're standing on the platform of a cosmic train station. Around you, trains of different types are departing for various destinations throughout the universe. Some carry sound waves, chugging along at a respectable but modest pace. Others bear light itself, racing away so quickly that they seem to vanish the instant they begin moving. But here's where our story becomes truly remarkable: that train carrying light isn't just fast, it represents something far more profound than mere speed. The velocity of light, roughly 300 million meters per second, isn't simply the universe's way of saying this is really, really quick. Instead, it's more like the universe's way of defining the very structure of reality itself. Think of it as the cosmic speed limit, but not in the way we usually think of speed limits. This isn't a rule imposed from outside, like a sign posted on a cosmic highway. Rather, it's woven into the fundamental fabric of space and time themselves. But why should there be any speed limit at all? After all, in our everyday experience, we can always imagine going faster. If you're walking, you can run. If you're running, you can ride a bicycle. If you're on a bicycle, you can hop in a car, from a car to a train, from a train to an airplane, from an airplane to a rocket. Each step seems to suggest that there's always a way to go faster, always another level of speed waiting to be achieved. So why should the universe suddenly say stop here, no further? The answer lies in understanding that space and time aren't the separate, independent things we once thought they were. Instead, they're intimately connected, woven together into what physicists call space-time. Picture, if you can, a vast fabric stretching in all directions, flexible and dynamic, capable of being stretched, compressed, and curved. This isn't just a metaphor. This fabric of space-time is as real as the ground beneath your feet or the air you breathe. When we begin to approach the speed of light, we're not just moving quickly through space, we're beginning to interact with the very structure of space-time itself in increasingly dramatic ways. It's rather like the difference between gently stirring honey with a spoon versus trying to stir it with a high-speed mixer. At slow speeds, the honey moves aside obligingly, but as you increase the speed, the honey begins to resist, becoming thicker, more viscous, pushing back against your efforts. Space-time behaves in a somewhat similar manner, though infinitely more subtle and strange. As objects accelerate toward light speed, space-time itself begins to respond, to change, to transform the very nature of time for that object. This isn't science fiction. This is the documented, measured, verified reality of our universe, tested thousands of times in laboratories around the world, and confirmed every single day by the GPS satellites orbiting our planet. Let's consider what happens to time as we approach this cosmic speed limit. Imagine you have an identical twin, and through some miraculous technology, one of you remains on Earth, while the other embarks on a journey at 90% the speed of light to a distant star. From Earth's perspective, your traveling twin's clocks would appear to run slower, not broken, not malfunctioning, but genuinely experiencing time at a different rate. If the journey took what appears to be 10 years from Earth's reference point, your twin would experience only about 4.5 years. They wouldn't feel like time was moving slowly, mind you. To them, seconds would still feel like seconds, minutes like minutes. But when they returned, they would have aged 4.5 years while you aged 10. This isn't theoretical anymore. It's been measured with atomic clocks on airplanes, observed in particle accelerators, and even detected in muons created by cosmic rays in our upper atmosphere. Now you might wonder, what if we could somehow push an object all the way to the speed of light itself? This is where things become truly extraordinary, and also where we encounter one of the universe's most fundamental limitations. As we approach light speed, several remarkable things begin to happen simultaneously, each more mind-bending than the last. First, time dilation becomes increasingly extreme. At 90% light speed, time runs at about half the normal rate. At 99%, it's down to about 14% of normal. At 99.9%, time crawls to just 4% of its usual pace. The pattern becomes clear. The closer we get to light speed, the more dramatically time slows down. But here's where mathematics reveals something truly extraordinary. At exactly the speed of light, time dilation becomes infinite. Time doesn't just slow down, it stops completely. From the perspective of a photon of light racing across the universe, no time passes at all between the moment it's emitted and the moment it's absorbed, regardless of whether that journey takes microseconds or billions of years from our perspective. Think about this for a moment. A photon leaving a distant star might travel for millions of years to reach your eye as you gaze up at the night sky. From your perspective, that light has been journeying across space for eons, crossing vast gulfs of emptiness, passing by countless other stars and planets. But from the photon's perspective, if we can even use such a term, the journey is instantaneous. It leaves the star and immediately arrives at your eye with no time having passed at all. This creates a fascinating paradox. When we consider what would happen if we could somehow accelerate a person to light speed, from our perspective, watching them, their time would slow down more and more until it finally stopped completely at the moment they reached light speed. But from their perspective, something even stranger would occur. The entire universe would seem to contract in the direction of their motion until distances became zero. This brings us to another fundamental transformation that occurs as we approach light speed: length contraction. Just as time dilates, space itself contracts. An object moving at high speed becomes shorter in the direction of its motion, not because it's being compressed by some external force, but because space itself is behaving differently. At 90% light speed, an object would contract to about 43% of its original length. At 99%, it would shrink to just 14%, and at light speed itself, the contraction becomes complete. The object's length in the direction of motion becomes zero. This isn't destruction or crushing, it's a fundamental property of how space and time work together. These effects, time dilation and length contraction, are not separate phenomena. They're two aspects of the same underlying reality, the structure of space-time itself. When we move through space, we're also moving through time, and the faster we move through space, the slower we move through time. The total speed through space-time remains constant, but the balance between spatial motion and temporal motion shifts. Imagine space-time as a highway with two lanes, one for motion through space, the other for motion through time. When you're sitting still, all your motion is through time. You're cruising in the time lane at maximum speed. But as you begin to move through space, some of your motion gets redirected into the space lane. The faster you go through space, the slower you go through time, always maintaining the same total speed through space-time. At light speed, all motion is through space and none through time. This is why photons don't age, don't decay, don't experience duration. They exist in a kind of eternal present, outside the flow of time as we understand it. They are, in a very real sense, timeless. But there's another aspect to approaching light speed that makes the journey even more impossible for objects with mass. The energy requirements become infinite. As an object accelerates, it gains kinetic energy, but at relativistic speeds, this energy doesn't just add to the object's speed, it also adds to its resistance to further acceleration. Think of it like trying to push a shopping cart that gets heavier every time you push it faster. At first, a gentle push accelerates it nicely, but as it speeds up, it gains mass, becoming harder to push. The faster it goes, the more massive it becomes, the more force you need to accelerate it further. Near light speed, this effect becomes so extreme that you'd need infinite energy to make the final push to light speed itself. This isn't a limitation of our technology or our understanding. It's a fundamental law of the universe. Only objects with zero mass, like photons, can travel at light speed, and they can never travel at any other speed. They must travel at light speed. It's their natural state of being. Everything else in the universe is forever limited to speeds less than light, always falling short of this cosmic boundary. The implications of this are profound and far-reaching. It means that information cannot travel faster than light, that cause and effect are limited by this cosmic speed limit, that the universe has a fundamental structure that prevents instantaneous communication across vast distances. When you look up at the night sky, you're not seeing the stars as they are now, but as they were when their light began its journey to your eyes. The nearest star beyond our sun, Proxima Centauri, is about 4 light-years away. When you see its light, you're seeing how it appeared 4 years ago. If Proxima Centauri suddenly exploded right now, we wouldn't know about it for 4 years. The light carrying that information would need that long to reach us, traveling at the universe's maximum speed. This creates what we might call the light speed horizon around every object in the universe. Information from beyond this horizon hasn't had time to reach us yet. As time passes, this horizon expands, allowing us to see further and further into the past of the universe. The most distant galaxies we can observe show us what the universe looked like billions of years ago, when it was young and very different from today. But let's return to the question of what happens to time at light speed. We've established that time stops for objects traveling at light speed. But what does this really mean? How can we understand this stopping of time in a way that makes intuitive sense? Consider the nature of time itself. In our everyday experience, time flows like a river, carrying us from past to future at a steady, unchanging rate. We measure it with clocks, schedule our lives around it, and experience it as the background against which all events unfold. But this intuitive understanding of time as a steady, universal flow turns out to be incomplete. Time is more flexible, more dynamic than we initially realized. It responds to motion, to gravity, to the structure of space-time itself. When we say time stops at light speed, we don't mean that clocks break or that processes cease. Instead, we mean that the rate at which time passes becomes zero relative to observers moving at slower speeds. Imagine watching a movie where the playback speed gradually slows down. At normal speed, actors move naturally, conversations flow, events unfold. Slow it down to half speed, and everything becomes languid, drawn out. Slow it further, to 10% speed, and motion becomes almost imperceptible. At 1%, it's practically frozen. At 0%, time in the movie has stopped completely, though the movie itself still exists, still contains all its information. It's just not progressing. This is analogous to what happens with time at light speed. From our perspective, time for a light speed object has stopped progressing, but this doesn't mean the object has ceased to exist, or that its properties have vanished. It means that its progression through time has become zero. For a photon racing across the cosmos, this creates a unique existence. It doesn't experience the journey, doesn't age during transit, doesn't have a before and after in its own reference frame. Its emission and absorption are the same event from its perspective, separated by zero time and zero distance. This might seem like a strange way for the universe to behave, but it serves important purposes in the cosmic order. The speed of light acts as a kind of cosmic traffic control system, ensuring that cause and effect maintain their proper relationship. That information propagates in an orderly fashion, that the universe maintains a coherent structure across vast distances and timescales. Without this speed limit, without the breaking of time at light speed, the universe would be a very different place. Events could influence each other instantaneously across any distance, causality would become muddled, and the orderly progression of time that allows for stable structures, complex chemistry, and ultimately life itself might not be possible. The speed of light isn't just fast, it's the speed at which the universe updates itself, the rate at which space and time maintain their relationship, the cosmic refresh rate that keeps reality coherent and consistent. When we approach this speed, we're not just moving quickly, we're approaching the fundamental operating frequency of reality itself. This brings us to another fascinating aspect of light speed, its role in defining the structure of space-time. In a universe without the speed of light limit, space and time might exist as separate, independent dimensions. But in our universe, they're unified into space-time, and the speed of light is the conversion factor between space and time measurements. When we measure distances in light years, we're using this conversion factor directly. A light year isn't just a distance, it's a distance defined by time and the speed of light. It's the distance light travels in 1 year, about 9,500,000,000,000,000 trillion meters. This unit reveals the deep connection between space and time, showing how they're really two aspects of the same fundamental reality. Similarly, when physicists measure very short times, they often convert them to distances by multiplying by the speed of light. A nanosecond, 1/1000,000,000th of a second, corresponds to about 30 centimeters at light speed. This isn't just a mathematical convenience, it reflects the underlying unity of space and time at the most fundamental level. The breaking of time at light speed also has profound implications for our understanding of simultaneity. In our everyday experience, we assume that now is universal, that there's a single absolute present moment that applies everywhere in the universe. But relativity shows us that simultaneity is relative, that what counts as now depends on your motion through space. Events that appear simultaneous to one observer may appear sequential to another observer moving at a different speed. This isn't a perceptual effect or an illusion, it's a fundamental property of space-time. The faster you move, the more your definition of simultaneity differs from that of slower-moving observers. At light speed, this effect becomes extreme. The concept of simultaneity loses meaning entirely. There is no now for a photon, no universal present moment in its reference frame. All of space contracts to zero length. All of time stops. The photon exists in a kind of eternal spaceless present that encompasses its entire journey instantaneously. This might sound abstract, but it has practical consequences. When we build GPS satellites, we have to account for the fact that they're moving fast enough relative to Earth's surface, that their clocks run slightly faster due to reduced gravitational time dilation, and slightly slower due to their orbital motion. These effects partially cancel each other, but the net result is that satellite clocks run about 38 microseconds fast per day compared to ground-based clocks. 38 microseconds might not sound like much, but light travels about 11 kilometers in that time. Without correcting for relativistic effects, GPS systems would accumulate errors of several kilometers per day, making them useless for navigation. The fact that your phone can tell you your location to within a few meters is direct proof that time behaves exactly as relativity predicts, including the strange behavior that occurs as we approach light speed. These time effects become even more dramatic in other situations. Particles called muons are created when cosmic rays hit our atmosphere at altitudes of about 15 kilometers. Muons are unstable and decay quickly, with a lifetime of only about 2/millionths of a second when at rest. At this rate, they should decay long before reaching Earth's surface, disappearing after traveling only a few hundred meters. But muons created by cosmic rays are moving at speeds very close to light speed, and time dilation extends their apparent lifetime dramatically. From our perspective, they live long enough to reach the ground, and be detected by instruments. From the Moon's perspective, its lifetime remains 2 millionths of a second, but the distance to Earth's surface contracts so much that the journey becomes possible. This is direct, measurable evidence of time breaking down as we approach light speed. The muons provide a natural experiment that confirms the predictions of relativity every day, as cosmic rays constantly bombard our atmosphere and create these high-speed particles that shouldn't survive their journey to Earth's surface, but do because of the strange behavior of time at near light speeds. The breaking of time at light speed also affects how we understand the expansion of the universe itself. The universe is expanding, meaning that distant galaxies are moving away from us, and the further away they are, the faster they're receding. At vast distances, this recession speed can approach the speed of light. Galaxies at the edge of the observable universe are moving away from us at speeds so close to light speed that their time appears almost stopped from our perspective. Light from these galaxies is redshifted to extremely long wavelengths, and the rate at which we receive information from them slows to a crawl. In effect, we're watching the early universe in extreme slow motion, seeing events that occurred billions of years ago, stretched out in time due to the relativistic effects of high-speed recession. This creates a kind of cosmic horizon, a boundary beyond which we cannot see because light from those regions hasn't had time to reach us and may never reach us if the expansion of space continues to accelerate. The speed of light limit doesn't just affect individual objects, it affects our ability to gather information about the universe as a whole. The concept of time breaking at light speed also raises fascinating questions about the nature of consciousness and experience. What would it be like to somehow experience motion at light speed? This question is ultimately unanswerable, because anything with consciousness, anything capable of experience, must have mass, and massive objects cannot reach light speed. But we can explore the question theoretically. As we approached light speed, our experience of time would remain normal to us. Seconds would still feel like seconds, thoughts would still progress at their usual pace, our hearts would still beat with familiar rhythm, but the outside universe would appear to change dramatically. As we accelerated toward light speed, we would see the universe ahead of us. Blue shift into higher and higher energy radiation, while the universe behind us would redshift into lower and lower energies. Distances would contract, making the journey to distant destinations shorter and shorter. At 90% light speed, a trip to a star 10 light-years away would only require traveling about 4.5 light-years from our perspective. But here's where the energy requirements make the scenario impossible. The energy needed to accelerate even a single gram of matter to near light speed is enormous. To accelerate a human being would require more energy than our entire civilization produces in a year. To reach exactly light speed would require infinite energy, which is simply impossible. This impossibility isn't a technological limitation, it's built into the fabric of reality itself. The universe prevents massive objects from reaching light speed, not through any external enforcement mechanism, but through the increasing energy requirements that become infinite at light speed. It's a self-regulating system, a natural law that maintains the cosmic order. The breaking of time at light speed also connects to some of the deepest mysteries in physics. When we try to understand what happens at the exact moment of light speed, we encounter mathematical infinities that signal the limits of our current understanding. These infinities suggest that light speed represents a fundamental boundary in nature, a place where our usual concepts of time, space, and causality reach their limits. Some physicists speculate that these infinities point toward deeper truths about the nature of reality. Perhaps space-time itself emerges from more fundamental processes that operate at scales where our current understanding breaks down. Perhaps the speed of light represents not just a speed limit, but a fundamental frequency at which reality operates, a cosmic heartbeat that drives the universe forward moment by moment. In quantum mechanics, we encounter similar mysteries. Particles can exist in superposition, being in multiple states simultaneously until observed. They can be entangled, sharing properties instantaneously, across vast distances in ways that seem to violate the light speed limit. Yet when we examine these phenomena carefully, we find that no information actually travels faster than light. No causality is violated. The universe maintains its cosmic speed limit, even in the quantum realm. The relationship between quantum mechanics and relativity, between the very small and the very fast, remains one of the great unsolved puzzles in physics. Both theories make predictions that have been verified to extraordinary precision, yet they seem to describe reality in fundamentally different ways. At light speed, where time breaks down, and at quantum scales, where certainty breaks down, we glimpse the edges of our current understanding. Perhaps the breaking of time at light speed is related to the breaking of classical logic in quantum mechanics. Perhaps both phenomena point toward a deeper reality, where time, space, matter, and information are unified in ways we haven't yet comprehended. The speed of light might be more than just a cosmic speed limit. It might be a window into the fundamental nature of existence itself. Consider the philosophical implications of time stopping at light speed. If time is how we measure change, duration, and sequence, what does it mean for time to stop completely? Does this suggest that light exists outside of time altogether? Are photons eternal in some sense, unchanging and timeless as they race across the cosmos? From one perspective, every photon that has ever existed, from the first light of the universe to the last photon that will be emitted before the heat death of the cosmos, exists in the same eternal present. They don't age, don't decay, don't experience duration. They are, in a sense, immortal participants in the cosmic drama, carrying information and energy across vast distances without themselves being changed by the journey. This timeless nature of light has practical consequences for how we understand the universe. When astronomers look at distant galaxies, they're not just seeing across space, they're seeing across time. The light they observe has been traveling for billions of years, but from the photon's perspective, the journey was instantaneous. In a very real sense, those ancient photons carry the past directly into our present without any intervening time. The cosmic microwave background radiation, the afterglow of the Big Bang itself, consists of photons that have been traveling for nearly 14 billion years, yet from their own perspective, they were emitted and detected in the same instant. They are direct messengers from the universe's infancy, carrying information across a temporal gulf that spans almost the entire history of the cosmos, yet experiencing no duration in their journey. This creates a beautiful paradox. The oldest light in the universe is also, from its own perspective, the youngest. Time and timelessness coexist in the same phenomena, depending on your frame of reference. The universe is simultaneously ancient and brand new, depending on whether you measure time from our perspective or from light's perspective. The breaking of time at light speed also affects how we think about the nature of space itself. In our everyday experience, space seems passive, a static stage on which events unfold. But relativity shows us that space is dynamic, capable of being curved, stretched, and compressed. Near light speed, these effects become extreme. Imagine riding a motorcycle down a long, straight highway. At normal speeds, the road seems static, unchanging, merely the surface on which you travel. But imagine if, as you accelerated, the road itself began to respond to your motion. The faster you went, the shorter the road would become, not because you were traveling faster, but because the road itself was contracting in response to your speed. This is analogous to what happens to space at high speeds. Distances genuinely contract, not because objects are being compressed, but because space itself behaves differently for objects in motion. At light speed, distances contract to zero. Space effectively disappears in the direction of motion. This spatial contraction is intimately connected to time dilation. Space and time trade off against each other as speed increases. The more space contracts, the more time dilates, maintaining a precise mathematical relationship that preserves the fundamental structure of space-time. At light speed, space contracts to zero and time dilates to infinity, two sides of the same cosmic coin. The speed of light also serves as a kind of cosmic constant, a fundamental parameter that defines the relationship between energy and matter. Einstein's famous equation, energy equals mass times the speed of light squared, shows that the speed of light is built into the very relationship between matter and energy. Every particle of matter contains enormous amounts of energy, locked up by the square of light speed. This relationship suggests that light speed isn't arbitrary. It's a fundamental property of reality that determines how matter and energy relate to each other. The breaking of time at light speed might be connected to this energy-matter relationship in ways we don't fully understand yet. Perhaps time itself is somehow energetic, and the infinite energy required to reach light speed is related to the infinite time dilation that occurs there. The speed of light also determines the strength of electromagnetic forces, the forces that hold atoms together and govern chemistry and biology. A universe with a different light speed would have different electromagnetic forces, different atoms, different chemistry, and presumably different forms of life if any life were possible at all. This suggests that the value of light speed isn't coincidental. It's part of a finely tuned set of cosmic parameters that makes our universe suitable for complexity, chemistry, and life. The breaking of time at this specific speed helps maintain the causal structure that allows stable atoms, molecules, and ultimately living systems to exist and evolve. In particle accelerators, physicists regularly accelerate particles to within tiny fractions of light speed, allowing them to directly observe time dilation and length contraction. These experiments provide some of the most precise confirmations of relativity available, measuring the effects of near-light speed motion with extraordinary accuracy. When protons are accelerated in the Large Hadron Collider, they reach speeds of about 99.999995% of light speed. At this speed, time dilation is so extreme that the protons experience only about 1/10,000th the passage of time that stationary observers experience. From the protons' perspective, their journey around the 27-kilometer circumference of the accelerator takes almost no time at all. These experiments also reveal another interesting aspect of approaching light speed: the distinction between coordinate time and proper time. Coordinate time is what we measure with our clocks as we watch the high-speed particles. Proper time is what a clock traveling with the particles would measure. As particles approach light speed, coordinate time continues normally, while proper time slows towards zero. At exactly light speed, proper time becomes zero. This is another way of understanding why time breaks at light speed, not because time stops everywhere, but because the proper time experienced by light speed objects becomes zero. Time continues normally for the rest of the universe, but for the light speed object, no proper time passes at all. This distinction between coordinate time and proper time is crucial for understanding relativity. Time doesn't stop absolutely at light speed, it stops relatively. The universe continues its normal temporal progression, but objects at light speed stop participating in that progression. They become frozen in their own temporal reference frame, while the rest of reality continues to evolve. The breaking of time at light speed also has implications for our understanding of entropy and the second law of thermodynamics. Entropy, the measure of disorder in a system, always increases over time in isolated systems. But what happens to entropy for systems at light speed where time stops? From one perspective, entropy becomes meaningless for light speed objects, because entropy requires time to have meaning. Without temporal progression, there's no before and after to compare, no way for entropy to increase or decrease. Light speed objects exist outside the normal flow of thermodynamic time. Yet from another perspective, light speed objects like photons do carry entropy in the form of information. A photon's energy, polarization, and other properties represent information that can be measured and quantified. This information travels at light speed without degrading, carrying entropy from its source to its destination instantaneously from the photon's perspective. This creates an interesting paradox. Photons are both outside the normal flow of thermodynamic time and fundamental carriers of thermodynamic information. They exist in a timeless state, yet facilitate the universe's progression toward higher entropy by carrying energy and information across vast distances. The concept of information traveling at light speed brings us to another important aspect of temporal breakdown: the relationship between causality and information. In our universe, nothing can carry information faster than light, which means that cause and effect are limited by the light speed barrier. This limitation creates the causal structure of space-time, determining which events can influence which other events. Two events can only be causally connected if light has enough time to travel between them. Events separated by distances greater than light could travel in the available time exist in what physicists call space-like separation, meaning they cannot influence each other. At light speed, this causal structure reaches its limit. Light itself defines the boundary between causally connected and causally disconnected events. The breaking of time at light speed is intimately connected to this causal structure, ensuring that information propagates in an orderly fashion and that the sequence of cause and effect remains coherent across the universe. Without this light speed limit, without the breaking of time that enforces it, causality could become muddled. Effects could precede their causes, information could propagate instantaneously, and the orderly progression of events that allows for stable physical laws and predictable behavior might not be possible. The speed of light acts as a kind of cosmic editing system, ensuring that the story of the universe unfolds in a coherent sequence. Each moment builds on the previous moment in a way that respects the causal relationships between events. The breaking of time at light speed serves as the ultimate enforcement mechanism for this cosmic narrative structure. This brings us to consider the role of light in defining the structure of the universe itself. Light doesn't just travel through space, it helps define what space means. The geometry of space-time is partially determined by how light behaves, how it curves around massive objects, how it redshifts as the universe expands, how it carries information about distant events. In general relativity, the path that light takes through curved space-time defines what we mean by straight lines. Light always travels along the shortest possible path through space-time, called a geodesic. These paths tell us about the curvature of space-time itself, revealing the presence of massive objects and the structure of the gravitational field. Near black holes, where space-time curvature becomes extreme, light paths bend dramatically. At the event horizon, the boundary around a black hole from which nothing can escape, light paths become so curved that they can no longer escape to distant observers. The breaking of time at light speed becomes entangled with the extreme curvature of space-time, creating regions where normal concepts of time and causality break down completely. Inside a black hole, beyond the event horizon, the roles of space and time become reversed in a sense. The radial direction, pointing toward the center of the black hole, becomes time-like, meaning that falling into the black hole becomes as inevitable as moving forward in time. The breaking of time at light speed contributes to this bizarre reversal of space and time roles. Yet even in these extreme environments, the fundamental speed limit remains. Nothing can travel faster than light, even in the curved space-time near black holes. The breaking of time at light speed continues to serve as a cosmic constant, maintaining the basic causal structure even where space and time behave in wildly unfamiliar ways. The study of black holes has revealed other connections between light speed and the nature of time. Hawking radiation, the theoretical emission of particles from black holes, involves processes that occur right at the edge of the event horizon, where light speed becomes crucial for determining what escapes and what remains trapped. The temperature of this Hawking radiation is inversely related to the black hole's mass, and the timescale for black hole evaporation depends on this temperature. For stellar mass black holes, this evaporation timescale is far longer than the current age of the universe, but for hypothetical microscopic black holes, evaporation could occur much more rapidly. The connection between light speed, time, and black hole physics suggests deep relationships between thermodynamics, gravity, and the fundamental structure of spacetime. The breaking of time at light speed might be connected to the thermodynamic properties of gravity itself, hinting at even more fundamental connections between space, time, matter, and information. These connections extend to cosmology. the study of the universe as a whole. The cosmic microwave background radiation provides a snapshot of the universe when it was only about 380,000 years old, the moment when it first became transparent to light. Before this time, the universe was so hot and dense that photons couldn't travel far before being absorbed and re-emitted by the hot plasma that filled space. The moment of transparency, called recombination, was when electrons and protons first combined to form neutral hydrogen atoms, allowing light to travel freely for the first time. This light has been traveling ever since, cooling and redshifting as the universe expands, carrying information about the early universe across nearly 14 billion years of cosmic history. From our perspective, this journey took almost the entire history of the universe, but from the photons' perspective, the journey was instantaneous. They were emitted in the early universe and detected by our instruments in the same moment of their own timeless existence. The cosmic microwave background represents a direct connection between the early universe and today, mediated by light that experienced no temporal duration in its cosmic journey. This creates a beautiful connection between the largest scales we can observe and the fundamental breaking of time at light speed. The entire observable universe is defined by how far light has been able to travel since the beginning of time, creating a cosmic horizon beyond which we cannot see. The breaking of time at light speed defines both the smallest scale of temporal experience, where photons exist in eternal presence, and the largest scale of cosmic observation, where light defines the boundaries of our observable universe. The expansion of the universe adds another layer to this story. As space itself expands, it carries galaxies away from each other at speeds that can exceed light speed for sufficiently distant objects. This doesn't violate relativity because it's space itself that's expanding, not objects moving through space faster than light. But this expansion does affect how we understand the breaking of time at light speed on cosmic scales. Light from the most distant galaxies has been traveling for billions of years, but during that time, space has been expanding, increasing the distance between us and those galaxies. The light we see today started its journey when those galaxies were much closer to us, and the galaxies we see are not where those galaxies are now. This creates a complex relationship between the timeless experience of light and the evolving structure of the universe. Light carries snapshots of cosmic history, frozen moments from different epochs of universal evolution, all arriving at our telescopes in an eternal now from the photon's perspective. The most distant galaxies we can observe appear as they were when the universe was only a few 100 million years old, still in its cosmic infancy, yet the light carrying this ancient information experiences no duration in its journey to us. In a very real sense, the early universe exists simultaneously with the present universe in the timeless realm of light-speed travel. This simultaneity of cosmic epochs creates a kind of temporal archaeology. When astronomers study distant galaxies, they're not just looking across space, they're excavating layers of cosmic time. Each distance corresponds to a different era in universal history, from the relatively recent past of nearby galaxies to the ancient past of the most distant objects we can detect. The breaking of time at light speed makes this cosmic archaeology possible. Without time dilation, without the timeless nature of light-speed travel, information from the early universe might not be preserved in transit. The photons might age or decay during their billion-year journeys, degrading the information they carry about cosmic history. Instead, light serves as a perfect preservative for cosmic information. The same physical processes that break time at light speed also ensure that photons carry their information unchanged across vast distances and durations. The universe's baby pictures, in the form of ancient light, arrive at our telescopes as crisp and clear as if they were taken yesterday. This preservation of information connects to deeper questions about the nature of reality itself. If information is fundamental to the universe, if reality is somehow computational or informational at its deepest level, then the speed of light might represent the universe's processing speed, the rate at which cosmic information can be updated and propagated. The breaking of time at light speed would then represent a fundamental limit on how quickly the universe can change, how fast new information can spread, how rapidly cause and effect can propagate through the cosmic network. Light speed becomes not just a velocity limit, but an information processing limit, a constraint on how quickly reality itself can evolve. This informational perspective on light speed has connections to modern theories about the nature of space and time. Some physicists propose that space-time itself might emerge from more fundamental informational processes, that space and time are not basic features of reality, but rather emergent properties of underlying information processing. In these theories, the speed of light represents the rate at which information can be processed and shared between different parts of the cosmic information network. The breaking of time at light speed marks the boundary where information processing becomes instantaneous, where the distinction between different locations in the network disappears. Such ideas remain highly speculative, but they suggest that the breaking of time at light speed might be connected to the deepest levels of reality, to the fundamental processes that give rise to space, time, matter, and energy. The cosmic speed limit might be more than just a physical constraint. It might be a window into the computational architecture of reality itself. These speculative connections bring us to consider how the breaking of time at light speed relates to our understanding of consciousness and observation. In quantum mechanics, the act of observation seems to play a special role in determining the behavior of particles. Some interpretations suggest that consciousness itself might be fundamental to how reality unfolds. If consciousness has a special relationship with time, if awareness requires temporal duration and sequence to exist, then the breaking of time at light speed might represent a boundary beyond which consciousness cannot exist. Light speed objects, existing outside the normal flow of time, might also exist outside the possibility of awareness or experience. This creates an interesting parallel between the physical impossibility of massive objects reaching light speed and the potential cognitive impossibility of consciousness existing at light speed. Both boundaries might reflect fundamental limitations built into the structure of reality, constraints that preserve the coherent operation of physical laws and conscious experience. The relationship between consciousness and time becomes even more intriguing when we consider how our brains process temporal information. Neural signals travel at speeds far slower than light, typically around 100 meters per second for the fastest nerve fibers. This means that consciousness operates in a temporal realm vastly removed from the timeless realm of light-speed phenomena. Our perception of simultaneity, our sense of now, is constructed by neural processes that integrate information arriving at different times from different senses and different parts of the body. The brain creates a coherent sense of present moment from inputs that actually arrive across a span of milliseconds. In a sense, consciousness already deals with the relativity of simultaneity on a neurological level. But the breaking of time at light speed represents something far more extreme than neural processing delays. It represents a complete cessation of temporal progression, a state where the very concept of experience becomes meaningless because experience requires time to unfold. This impossibility of conscious experience at light speed might be related to the physical impossibility of reaching light speed. Perhaps consciousness and matter share fundamental properties that make light speed a boundary for both. Perhaps the breaking of time at light speed serves to preserve not just physical causality, but also the possibility of awareness and experience. The study of particle physics provides another window into the breaking of time at light speed. In particle accelerators, scientists routinely create conditions where time dilation becomes significant, where particles live longer than they should due to their high-speed motion, where the effects of approaching light speed become measurable and predictable. These experiments reveal that time dilation isn't just a curious side effect of high speeds, it's a fundamental aspect of how reality operates at the deepest level. Unstable particles that should decay quickly live much longer when accelerated to near light speeds, not because the physical processes governing their decay have changed, but because time itself is passing more slowly for them. This time dilation can be so extreme that particles created in accelerator collisions survive long enough to travel distances they could never cover at rest. particles that live for billionths of a second when stationary can travel meters or even kilometers when accelerated to near light speed, their lifetimes extended by the strange behavior of time at high velocities. These observations provide direct, measurable evidence that time is not absolute, not universal, not independent of motion. Time is dynamic, relative, intimately connected to space and motion in ways that become increasingly dramatic as we approach light speed. The breaking of time at light speed is not theoretical speculation. It's a measured, verified aspect of how our universe actually works. The implications extend beyond particle physics to our understanding of the evolution of the universe itself. In the early moments after the Big Bang, when the universe was incredibly hot and dense, particles were moving at speeds close to light speed. Time dilation effects would have been significant, affecting how quickly physical processes could occur, how rapidly the universe could cool and evolve. The breaking of time near light speed might have played a crucial role in determining the rate at which the early universe expanded, cooled, and developed structure. The fundamental forces that govern particle interactions operate according to timescales that would have been affected by the high-speed motion prevalent in the early cosmos. As the universe expanded and cooled, average particle speeds decreased, time dilation effects became less significant, and the cosmos entered a regime where time flows more uniformly. But the legacy of those early moments, when time behaved very differently due to the extreme conditions, is preserved in the large-scale structure of the universe we observe today. The cosmic microwave background radiation carries subtle patterns that reflect these early temporal effects. The tiny fluctuations in temperature across the sky represent density variations that were present when the universe first became transparent to light. These variations were influenced by the complex interplay between matter, energy, and space-time in an environment where relativistic effects were much more significant than they are today. By studying these patterns, cosmologists can reconstruct the conditions in the early universe, including the role that time dilation and other relativistic effects played in shaping cosmic evolution. The breaking of time at light speed isn't just a curiosity of modern physics, it's a fundamental aspect of cosmic history that continues to influence the structure and evolution of the universe. This historical perspective on relativistic effects brings us to consider how our understanding of time and light speed has evolved. For most of human history, time seemed absolute and universal, flowing at the same rate everywhere and for everyone. Light seemed instantaneous, or at least so fast that its finite speed was imperceptible in everyday experience. The realization that light has a finite speed came gradually through careful observations of astronomical phenomena. The timing of eclipses of Jupiter's moons, observed from different points in Earth's orbit, revealed that light takes measurable time to cross the solar system. This was one of the first hints that the universe operates according to a cosmic speed limit. But it took Einstein's insights to reveal that this speed limit is not just a property of light, but a fundamental feature of space-time itself. The speed of light in vacuum represents the maximum rate at which information, energy, or causal influence can propagate through the universe. This limit shapes the structure of space and time in ways that become increasingly dramatic as we approach it. The breaking of time at light speed represents the ultimate expression of this cosmic speed limit. It's not just that nothing can go faster than light, it's that at light speed itself, the normal flow of time ceases, space contracts to zero, and the familiar concepts of duration and distance lose their meaning. This transformation of our understanding represents one of the most profound shifts in human thought about the nature of reality. The universe revealed itself to be far stranger, far more interconnected, and far more unified than anyone had imagined. Space and time, seemingly separate and independent, turned out to be aspects of a single dynamic entity. Matter and energy, apparently distinct, proved to be different forms of the same underlying reality. The speed of light became the conversion factor between these different aspects of reality, the fundamental constant that determines how space relates to time, how matter relates to energy, how information propagates through the cosmos. The breaking of time at light speed marks the boundary where these relationships become infinite. where our normal categories of thought reach their limits. Yet this boundary is not arbitrary or artificial. It emerges naturally from the structure of reality itself, from the way that space, time, matter, and energy are woven together into the fabric of existence. The cosmic speed limit is not imposed from outside, it arises inevitably from the internal logic of space-time. This internal logic has practical consequences that extend far beyond academic physics. The GPS satellites orbiting Earth must account for relativistic time dilation, or their navigation signals would quickly become inaccurate. Particle accelerators must account for the increasing energy requirements as particles approach light speed. Medical imaging techniques that use high-energy radiation depend on our understanding of how particles behave at relativistic speeds. Even the nuclear processes that power the sun depend on the relationship between matter and energy expressed in Einstein's famous equation. The breaking of time at light speed is not just a theoretical curiosity, it's woven into the technological infrastructure of modern civilization and the fundamental processes that sustain life on Earth. The sun converts matter into energy at a rate of about 4 million tons per second, following the relationship defined by the speed of light squared. This enormous conversion factor, about 90 quadrillion joules per kilogram, explains how relatively small amounts of matter can produce the vast quantities of energy that power our solar system. The light that results from these nuclear processes travels from the sun's core to its surface over the course of thousands of years, bouncing randomly between atoms in the dense solar interior. But once it escapes from the sun's surface, it races across the 150 million kilometers to Earth in just over 8 minutes, experiencing no time in its own reference frame during this journey. From the photon's perspective, its creation in the solar core and its absorption in your eye when you see sunlight are the same event, separated by zero time and zero distance in its own frame of reference. The thousands of years spent bouncing around inside the sun, the 8-minute journey through space, the passage through Earth's atmosphere, all collapse into a single instantaneous moment from the light's point of view. This creates a beautiful connection between the microscopic quantum processes in the sun's core and the macroscopic experience of feeling sunlight on your skin. The breaking of time at light speed bridges these scales, carrying energy from nuclear fusion directly to biological systems without any temporal duration from the photon's perspective. The same principle applies to all electromagnetic radiation, from radio waves to gamma rays. All forms of light travel at the same speed in vacuum and experience the same breaking of time. A radio wave from a distant pulsar, carrying information about exotic physics in neutron star magnetospheres, experiences no duration in its journey across thousands of light-years of interstellar space. This universality of light speed for all electromagnetic phenomena reveals something profound about the structure of physical law. The breaking of time doesn't depend on the energy or frequency of light. It's a universal property of all electromagnetic radiation. This suggests that the phenomenon is not specific to light itself, but rather reflects something fundamental about the nature of space-time. Indeed, anything traveling at light speed would experience the same breaking of time, whether it's a photon, a gravitational wave, or any hypothetical massless particle. The speed limit is not specific to electromagnetism. It's a property of space-time itself that affects all forms of energy and information. Gravitational waves, ripples in the fabric of space-time itself, also travel at light speed. When massive objects like black holes or neutron stars orbit each other rapidly, they create distortions in space-time that propagate outward at exactly the speed of light. These waves experience the same time dilation, the same breaking of temporal progression that affects photons. The recent detection of gravitational waves by instruments like LIGO has provided new confirmation of these principles. The gravitational waves from colliding black holes billions of light-years away reached Earth having experienced no proper time during their journey. From their perspective, they were created and detected simultaneously, despite traveling across vast reaches of cosmic space and time. This detection of gravitational waves also revealed new aspects of how the breaking of time at light speed affects the propagation of information. The gravitational waves from black hole mergers arrived at Earth within seconds of the gamma-ray bursts produced by the same events, confirming that both forms of radiation travel at precisely the same speed. This simultaneity provides powerful evidence that the speed of light is truly universal, that it applies not just to electromagnetic phenomena, but to all forms of energy and information propagation. The breaking of time at this speed is a fundamental feature of reality that governs how the universe communicates with itself across vast distances. The study of gravitational waves has also revealed how the breaking of time at light speed affects our ability to study extreme gravitational environments. The waves carry information about conditions near black holes and neutron stars, regions where space-time is so severely curved that normal concepts of space and time break down. Yet even in these extreme environments, the fundamental speed limit remains. Information about these exotic conditions can only reach us at light speed, carried by gravitational waves or electromagnetic radiation that experience no proper time during their journey. The breaking of time at light speed serves as a universal postal service for the cosmos, delivering information about extreme physics across the universe. This informational role of light-speed phenomena connects to deeper questions about the relationship between physics and information theory. Some physicists argue that information is more fundamental than matter or energy, that the universe is essentially computational in nature, processing information according to physical laws. In this view, the speed of light represents the universe's processing speed, the maximum rate at which information can be computed and communicated. The breaking of time at light speed marks the boundary where information processing becomes instantaneous, where the computational delay between cause and effect approaches zero. This computational perspective on physics suggests that the universe might be understood as a vast information processing system, with particles and fields serving as hardware for cosmic computation. The speed of light would then represent not just a physical limit, but a computational limit, determining how quickly the universe can update its state and propagate changes throughout the system. Such ideas remain highly speculative, but they highlight how the breaking of time at light speed connects to some of the deepest questions in physics and philosophy. What is the relationship between information and reality? Is the universe fundamentally computational? How do physical laws emerge from more basic informational processes? These questions become particularly intriguing when we consider the quantum mechanical aspects of light and other high-speed phenomena. Quantum mechanics tells us that particles can exist in superposition, being in multiple states simultaneously until observed. But how does this quantum behavior relate to the relativistic effects that occur at high speeds? When particles are accelerated to near light speed, they still exhibit quantum behavior, but this behavior becomes increasingly difficult to observe due to the extreme time dilation. From our perspective, quantum processes in high-speed particles appear to slow down along with everything else. But from the particle's perspective, quantum processes continue at their normal rate. This creates interesting questions about the relationship between quantum measurement and relativistic time dilation. If observation is required to collapse quantum superpositions, and if time dilation affects the rate at which observations can occur, then relativistic effects might influence quantum behavior in subtle ways. At light speed itself, where time stops completely, quantum processes would also appear to stop from our perspective. But this raises puzzling questions about the quantum nature of light itself. Photons are quantum objects, exhibiting wave-particle duality and other quantum properties. How do these quantum properties relate to the breaking of time that occurs at light speed? The answer seems to be that quantum properties are preserved even when time stops. A photon maintains its energy, momentum, polarization, and other quantum properties throughout its journey, regardless of how long that journey takes from our perspective. The breaking of time at light speed doesn't eliminate quantum behavior, it preserves it in a kind of temporal stasis. This preservation of quantum properties during light speed travel has important implications for quantum information theory. quantum information can be encoded in photons and transmitted at light speed without degradation. The breaking of time at light speed actually helps preserve quantum information, preventing it from being corrupted by environmental interactions during transmission. This is why photons are ideal carriers for quantum communication systems. They can carry quantum information across vast distances without the information being lost or altered. The same temporal stasis that stops time for photons also preserves their quantum states, making them perfect messengers for quantum information. The relationship between quantum mechanics and relativity at light speed also raises questions about the nature of quantum entanglement. When particles become entangled, they share quantum properties in ways that seem to allow instantaneous correlation across any distance. This appears to violate the light speed limit on information transmission. However, careful analysis shows that no actual information is transmitted faster than light through quantum entanglement. The correlations are instantaneous, but they cannot be used to send messages or signals faster than light speed. The breaking of time at light speed is preserved even in the quantum realm. This preservation of the light speed limit in quantum mechanics suggests that the breaking of time at light speed is truly fundamental, applying to all aspects of physics, both classical and quantum. It's not just a property of classical spacetime, but a feature of reality at the deepest level we can currently probe. The study of quantum field theory, which combines quantum mechanics with special relativity, has revealed even deeper connections between the breaking of time at light speed and the fundamental structure of reality. In quantum field theory, particles are understood as excitations in underlying fields that fill all of space. These fields propagate information and energy at light speed, with disturbances in one location affecting distant locations only after light has had time to travel between them. The breaking of time at light speed ensures that these field disturbances maintain proper causal relationships, preventing effects from preceding their causes. The vacuum itself, empty space, is understood in quantum field theory to be filled with these fields in their lowest energy states. Even empty space is alive with quantum activity, with virtual particles constantly appearing and disappearing on timescales so short that they cannot be directly observed. But even these quantum vacuum fluctuations respect the light speed limit, with correlations between fluctuations at different locations limited by light travel time. This quantum view of empty space suggests that the speed of light is built into the very structure of the vacuum. That empty space itself has properties determined by the cosmic speed limit. The breaking of time at light speed is not just something that happens to objects moving through space, it's a fundamental feature of space itself. The relationship between quantum fields and light speed also explains why the speed of light has the value it does. In quantum field theory, the speed of light emerges from the properties of the electromagnetic field and its interactions with other fields. The specific numerical value, about 300 million meters per second, is determined by the strength of electromagnetic interactions and the structure of space-time. This suggests that the breaking of time doesn't occur at an arbitrary speed, but at a speed determined by the fundamental constants that govern electromagnetic interactions. The value of light speed is intimately connected to the strength of electric and magnetic forces, the charge of the electron, and other basic parameters of particle physics. These connections highlight how the breaking of time at light speed is woven into the entire fabric of physical law. It's not an isolated phenomenon, but part of an interconnected web of relationships that determines how matter, energy, space, and time behave throughout the universe. The study of these interconnections has led to attempts to unify all the fundamental forces of nature into a single theoretical framework. In these unified theories, the breaking of time at light speed would emerge as a natural consequence of the deep symmetries that govern all physical interactions. Such theories remain incomplete, but they suggest that the phenomena we observe at light speed might be windows into even more fundamental aspects of reality. The breaking of time might be connected to the breaking of other symmetries, to phase transitions in the structure of space-time itself, to the emergence of the familiar forces and particles from more exotic underlying structures. These speculative connections bring us full circle to the wonder and mystery that originally drew us to consider the breaking of time at light speed. Despite all our scientific advances, despite our ability to measure and predict relativistic effects with extraordinary precision, the phenomenon remains profoundly mysterious and beautiful. The fact that time can slow down, stop, and behave in such unexpected ways challenges our most basic intuitions about the nature of reality. Yet these challenges have led to deeper understanding, to more complete theories, to practical technologies that improve human life. The breaking of time at light speed is both utterly alien to everyday experience and intimately connected to the technologies we use every day. Perhaps this is the most remarkable aspect of the phenomenon, how something so counterintuitive, so removed from ordinary experience, can be so fundamental to the operation of the universe. The GPS satellite that helps you navigate uses corrections for time dilation. The particle accelerator that produces medical isotopes relies on relativistic effects. Even the nuclear fusion in stars depends on the relationship between matter and energy expressed through the speed of light. The breaking of time at light speed is not just a curious theoretical prediction. It's an essential feature of the universe that makes possible the complex structures and processes that sustain life. Without this cosmic speed limit, without the strange behavior of time at high speeds, the universe might be a very different and much less interesting place. This practical importance of seemingly abstract physics reflects a deeper truth about the nature of scientific discovery. The most fundamental insights often seem completely divorced from practical application when first discovered, yet they frequently turn out to be essential for understanding and manipulating the natural world. Einstein's insights about the breaking of time at light speed seemed purely theoretical when first proposed. Today they're essential for everything from GPS navigation to medical imaging to our understanding of stellar evolution. The abstract mathematics of relativity has become the practical foundation for countless technologies. This pattern suggests that our current frontiers in understanding the breaking of time at light speed, including speculative ideas about quantum gravity and the computational nature of reality, might someday prove to have practical applications we cannot currently imagine. The universe has a way of turning today's impossibly abstract concepts into tomorrow's essential technologies. The breaking of time at light speed also serves as a reminder of how much we still don't understand about the nature of reality. Despite our sophisticated theories and precise measurements, we still cannot answer fundamental questions about why time behaves as it does, why the speed of light has the value it has, or how consciousness relates to the physical processes we observe. These limitations in our understanding are not failures, they're invitations. They point toward deeper mysteries waiting to be explored, more fundamental truths waiting to be discovered. The breaking of time at light speed is both an achievement of human understanding and a signpost pointing toward even greater mysteries. As we continue to explore these mysteries, we might discover that the breaking of time at light speed is just one aspect of an even more remarkable and beautiful underlying reality. Perhaps time and space are emergent properties of more fundamental processes. Perhaps consciousness and matter are different aspects of the same underlying information. Perhaps the universe is far stranger and more wonderful than we can currently imagine. But even if our understanding remains incomplete, even if greater mysteries await, the phenomenon of time breaking at light speed stands as one of the most profound and beautiful discoveries in human history. It reveals a universe that is both rationally comprehensible and utterly mysterious, both mathematically precise and poetically beautiful. In the end, perhaps this is the most important lesson from studying the breaking of time at light speed, that the universe is both knowable and mysterious, both familiar and alien, both simple in its fundamental laws and infinitely complex in their consequences. The cosmic speed limit that breaks time also connects us to the deepest truths about existence, making us part of the same vast interconnected web of space, time, matter, and energy that encompasses everything from the smallest quantum fluctuations to the largest structures in the observable universe. As photons race across the cosmos, experiencing no time in their eternal present, They carry not just energy and information, but also the possibility of understanding, the potential for consciousness to comprehend the very universe that gave it birth. In studying how time breaks at light speed, we are not just learning about physics, we are participating in the universe's attempt to understand itself. And in that participation, in that moment of comprehension, when the strange behavior of time at light speed becomes clear, we experience something that might be as close to the timeless realm of light as conscious beings can get. We transcend our limited perspective, our brief existence, and touch something eternal and universal. We become, for a moment, citizens of the cosmos, understanding our place in the vast, beautiful, and utterly mysterious reality we call home. The journey continues, the exploration deepens, and the mysteries multiply even as understanding grows. The breaking of time at light speed is both destination and departure point, both answer and question, both ending and beginning, in the endless human quest to comprehend the nature of existence itself. In the timeless realm of light, past and future collapse into an eternal now, and in that eternal now, the possibility of understanding shines as brightly as the stars themselves, illuminating the path toward ever deeper truths about the magnificent universe we are privileged to inhabit and explore. Through the gentle rhythm of discovery and wonder, through the patient accumulation of insight, and the sudden flashes of understanding, through the careful measurements and the bold theoretical leaps, humanity continues its ancient dialogue with the cosmos, and at light speed, where time breaks and eternity begins, that dialogue reaches towards something approaching completion, toward a moment of perfect understanding, where consciousness and cosmos, observer and observed, knower and known, merge into a single, timeless, transcendent truth. The speed of light stands not just as a cosmic speed limit, but as an invitation to transcendence, a gateway to understanding that connects the smallest scales of quantum reality to the largest scales of cosmic evolution. In the breaking of time at light speed, we glimpse the face of infinity, and in that glimpse, we find not just knowledge but wisdom, not just facts but meaning, not just understanding but peace. As the journey through space and time continues, as photons carry their timeless messages across the expanding universe, as consciousness contemplates its own existence within the vast web of causality and connection that links all things, the breaking of time at light speed remains a constant reminder that reality is far more beautiful, far more mysterious, and far more wonderful than we ever dared imagine. In this realization, in this moment of cosmic humility and cosmic awe, we find perhaps the deepest truth that the breaking of time at light speed has to teach us that we are part of something infinitely larger than ourselves, something so beautiful and so mysterious that even our most profound insights serve only to deepen the mystery, to expand the wonder, to multiply the questions that draw us ever forward in our eternal quest to understand the nature of existence itself. And so the story continues, the exploration deepens, and the mystery grows more beautiful with each new discovery, each new insight, each new question that arises from our contemplation of how time breaks at the speed of light, carrying us forward on waves of understanding toward horizons we cannot yet imagine, toward truths we cannot yet conceive, toward a future where the breaking of time at light speed may prove to be just the beginning of an even more remarkable and beautiful story about the nature and destiny of consciousness in an infinite, eternal, and utterly mysterious cosmos. The contemplation of these cosmic mysteries brings us to a more intimate understanding of our own place in this vast tapestry of existence. Each breath you take, each heartbeat, each thought that passes through your mind exists within the framework established by the breaking of time at light speed. The very atoms that comprise your body were forged in the hearts of ancient stars, where nuclear processes operated according to the same relativistic principles we've been exploring. Consider the iron in your blood, created in the final moments of a massive star's life, when temperatures and pressures became so extreme that time itself behaved very differently from our everyday experience. Those iron atoms have journeyed across space for billions of years, traveling in the light-speed realm of photons and cosmic rays, experiencing the strange temporal effects we've been discussing. When that ancient star exploded in a supernova, It scattered its elements across space in a blast of energy that reached temperatures where relativistic effects dominated. The heavy elements that would eventually become part of planets, and ultimately part of you, were created in environments where time dilation was significant, where the breaking of time at light speed played a crucial role in determining which nuclear reactions could occur. The calcium in your bones, the oxygen you breathe, the carbon that forms the backbone of every molecule in your body, all these elements have their origins in stellar furnaces, where the physics of light speed determined their very existence. You are quite literally made of stardust that has experienced the strange temporal effects of near light speed motion during its cosmic journey to Earth. This connection between the breaking of time at light speed and the chemical composition of your body reveals something profound about the relationship between the abstract principles of physics and the concrete reality of existence. The same mathematical relationships that govern time dilation and length contraction also governed the nuclear processes that created the elements essential for life. The universe operates as an integrated whole, where the behavior of time at light speed connects intimately to the possibility of complexity, chemistry, biology, and ultimately consciousness. The cosmic speed limit doesn't just affect exotic particles in accelerators or light from distant galaxies, it shapes the fundamental processes that make life possible. Even the energy that powers your thoughts right now comes from food, which ultimately derives its energy from sunlight, which was created in nuclear fusion reactions in the sun's core according to the same principles that relate matter and energy through the speed of light. The equation that describes this relationship, with the speed of light squared as the conversion factor, determines how much energy is available to power the biochemical processes of life. Your brain, processing these words, extracting meaning from patterns of language, creating understanding from information, operates according to principles that are ultimately grounded in the same physical laws that cause time to break at light speed. The electrical signals racing through your neurons, the chemical reactions that sustain consciousness, the quantum processes that might underlie thought itself, all exist within the framework established by the cosmic speed limit. This creates a beautiful recursive relationship, consciousness, arising from processes governed by the speed of light. Contemplating the breaking of time at light speed, the universe has become self-aware through beings like us, and that self-awareness includes the capacity to understand the very physical principles that made consciousness possible in the first place. The breaking of time at light speed is not just something we observe from the outside, it's woven into the fabric of our existence, built into the foundation of every process that sustains life and consciousness. We are not separate from these cosmic principles, we are manifestations of them, expressions of the same underlying reality that causes time to behave so strangely at the speed of light. This realization transforms how we might think about our relationship to the cosmos. We are not insignificant specks in a vast, indifferent universe, but rather the universe's way of understanding itself, consciousness emerging from the same physical principles that govern the behavior of light and time across cosmic scales. The breaking of time at light speed helped create the conditions that made our existence possible, and now our existence allows the universe to contemplate its own nature. The photons that left distant stars billions of years ago, traveling through their timeless existence, carry information that our consciousness can interpret and understand. In the act of observation, of measurement, of comprehension, we complete a cosmic circuit that connects the timeless realm of light speed travel to the temporal realm of conscious experience. When you look up at the night sky and see the light from distant stars, you are participating in a process that bridges different modes of existence. The photons racing toward your eyes experience no time during their journey, but when they interact with the neurons in your retina, they enter the temporal world of biological processes, where seconds and minutes and lifetimes have meaning. This transition from the timeless realm of light to the temporal realm of consciousness represents one of the most remarkable transformations in nature. Information that has existed in a kind of eternal present suddenly enters the flow of time, becoming part of the ongoing process of thought, memory, and understanding that characterizes conscious experience. The boundary between these realms, between the timeless and the temporal, occurs whenever light interacts with matter, whenever photons are absorbed or emitted, whenever electromagnetic radiation couples with the charged particles that make up atoms and molecules. This boundary is everywhere, constantly crossed, constantly renewed, creating an ongoing dialogue between different aspects of reality. In biological systems, this dialogue becomes particularly rich and complex. The processes of photosynthesis, for example, involve the absorption of timeless photons by molecular structures that channel their energy into the temporal world of biochemistry. Plants capture light that has experienced no duration in its journey from the sun and convert it into chemical energy that powers growth, reproduction, and all the other processes that unfold over time. This conversion from timeless energy to temporal processes is one of the most fundamental operations in biology, creating the bridge between the physical universe and the living world. The breaking of time at light speed is not separate from life, it's essential to life, providing the energy that powers biological processes and the information that guides biological development. Even more remarkably, some biological processes seem to exploit quantum mechanical effects that depend on the precise timing relationships established by the speed of light. Photosynthesis, for instance, appears to use quantum coherence effects to optimize energy transfer efficiency, taking advantage of the quantum properties of light to maximize the capture of solar energy. These quantum biological processes represent another layer of connection between consciousness and the breaking of time at light speed. The quantum effects that make these processes possible depend on the same fundamental principles that cause time dilation and length contraction at high speeds. Life doesn't just depend on the products of stellar nucleosynthesis, it actively exploits the quantum mechanical aspects of the electromagnetic field. The study of these quantum biological effects has revealed that living systems are far more sophisticated than previously imagined, capable of maintaining quantum coherence at biological temperatures and timescales in ways that seemed impossible just a few decades ago. Life has apparently learned to work with the fundamental principles of physics, including those related to the speed of light, in ways that maximize efficiency and functionality. This suggests that the relationship between life and the breaking of time at light speed goes beyond mere dependence on stellar nucleosynthesis or solar energy. Life appears to be intimately adapted to the quantum mechanical and relativistic properties of the universe, exploiting these properties to achieve remarkable feats of organization and complexity. The evolution of consciousness might represent the ultimate expression of this adaptation, creating beings capable of understanding and manipulating the very principles that govern their existence. In developing the ability to comprehend the breaking of time at light speed, consciousness has achieved a kind of cosmic self-awareness, where the universe becomes capable of understanding its own fundamental nature.